Welcome to the HasMotion YouTube channel. In today's video, we will be describing how to modify the plug and gait lower body model we built in our previous video to account for errors in the marker set. Sometimes a limited marker set or erroneous marker placement can lead to incorrect segment appearances and definitions. Here we'll show you what changes can be made for the data we used to build the original model. Links to the original video and the corresponding webpage for this tutorial can be found in the description. Our updated lower body model includes several modifications that have been made to our original model due to errors present in the marker set. These modifications include an updated shank definition using a knee marker as a lateral boundary, a new foot definition with a new toe marker added, and a different pelvis definition using 4 targets. This tutorial uses the same marker set as the original plug and gait lower body model, consisting of 12 total markers and 6 for each leg. The necessary static files to build this model can be found via the wiki link in the description. You do not need to re-download these files if you're continuing from the previous video. We'll begin building the model by loading the static file included in the data on the wiki page. From the model menu, select Hybrid Model from C3D file and select the appropriate calibration file. Select walking file static lower body.c3d and apply it to all of the movement trials. Now we can start defining our segments by creating important model metrics like height, weight, and joint radii. We'll be defining all of these subject metrics the same way as we did for the original lower body model. Click the Subject Data/Metrics button, select Mass, and click the Modify Selected Item button. Change the value to 75. Next, select the subject metric for height and change the value to 1.75. This is our subject's height in meters. Add a new item with the name marker radius and set the value to 0.005. Once this is done, we can create an item named left knee width with a value of 0.105 and a matching item named right knee width. These items indicate the width of the knee joint for the subject. We'll also make a new item named knee width. That's an average of the 2 knee widths defined by the expression left knee width plus right knee width divided by 2. Now create left and right ankle width with a width of 0.070 and a matching ankle width value that averages the two the same as we did for the knees. Now we can start defining the landmarks that we'll use to make our segments. We'll start by creating the landmarks that we need to define our pelvis segment. This segment is defined by 4 targets. For an alternative pelvis definition with 3 targets, see the original tutorial. First, create the SCRM. Click the Landmarks button, add a new landmark with the name SCRM. Define using the RPSI as a starting point, LPSI as an ending point, and use the following medial, lateral, anterior, posterior, and axial offsets. An axial offset of 0.5 will be needed. Check offset by percent 1.0 and calibration only landmark. This is the only landmark we'll need to define our pelvis. The rest of the segment will be defined by markers. Now we can create the actual segment by navigating to the Segments tab, selecting Pelvis in the segment name box, and selecting Coda as the segment type. To define the segment, we'll change the RPSIS to SCRM and the LPSIS to SCRM. We'll also use tracking targets instead of the calibration signals. Select tracking targets as LASI, LPSI, RASI, and RPSI. One thing I missed, but you'll want to do, is change the ACES target radius to the marker radius definition that we defined earlier. Now we'll navigate back to the Subject Data/Metrics tab and create a new value named left leg length. This will be defined as 0.940 or using an expression as the distance between the LASI and LANK. Create the right leg length and define it the same way. We'll also add a new metric named leg length and define it as an average of the two leg lengths we just made. Next, we'll create a new value named c with the expression 0.115 times leg length minus 0.0153. Now we'll create theta and define it as 28.4 times pi divided by 180, and create beta, which is defined as 18 times pi divided by 180. The next metric is named xdis, which we'll define as 0.750 or as 0.12288 times leg length minus 0.04856. Now we'll create three new metrics named HJC underscore ML, HJC underscore AP, and HJC underscore AX, which are all defined using those three metrics we just created. Feel free to pause the video to get down the definitions as shown on the screen. Now that all the necessary subject metrics have been created, we can go back to building the landmarks needed to define our model. Create a new landmark named RHJC. This will be defined using the existing pelvis segment and using offsets in the x direction of negative HJC underscore ML, in the y direction HJC underscore AP, and in the z direction or axial direction of HJC underscore AX. Build this landmark, and then you can copy and reflect it to build the corresponding left hip joint center. We'll now use these new landmarks to create the thigh segment. In the Segments tab, create right thigh and define it using a proximal joint center at the right hip joint center and a radius of 0.5 times the distance of right hip joint center to the left hip joint center. Define the distal joint center with a lateral marker at the right knee and a radius of 0.5 times the knee width plus the marker radius. Use an extra target to define the segment with a lateral target at the right thigh and use calibration targets for tracking. Again, you can copy and reflect this segment for the left thigh, and then we'll move on to making the landmarks necessary to build our shank segment. Create a new landmark named RKJC, or right knee joint center. Define this using the existing right thigh segment and an axial offset of -1. Check offset by percent 1.0 and build the model. This can be copied and reflected again to build the left knee joint center. In the Segments tab, enter right shank in the segment name box and click Create Segment. We'll define this using a lateral marker at the distal point of the right knee and a joint center of the right knee joint center. At the distal center, we'll use a lateral marker of the right ankle and a radius of 0.5 times the ankle width plus the marker radius. We'll use calibration signals for tracking. Once you have built the model, you can copy and reflect it for the left shank. We'll now create our foot landmarks, starting with the right ankle joint center. Click the Landmarks button, add a new landmark named RAJC, and define it using the existing right shank center. Use an axial offset of -1.0 and check the offset by percent 1.0 button. Again, copy and reflect this for the left ankle joint center. Next, we'll create another landmark at the right toe in the z-axis. We'll name this landmark r underscore toe underscore z and define it using the existing lab coordinate system. Offset using a -0.1 offset in the z direction and check calibration only landmark. This can also be copied and reflected for the left toe. We can now create the right foot segment in the Segment Names tab by adding the right foot in the name box. Create the segment and define it using a proximal joint center of the right ankle joint center and a radius of the right shank distal radius. We'll define the distal joint center using right toe marker and a radius again of the right shank distal radius. We use an extra signal to define it in the posterior axis using a right toe Z marker we just created. We'll define this using tracking targets at the right heel, the right fifth metatarsal, and the right toe. Click on Build Model and close tab, and you can copy and reflect this for the left foot. Finally, we'll create our virtual foot segments, which are made to better align the foot kinematics with the lab. In the Segments tab, type right virtual foot and check Kinematic only. Create the segment and define it using a proximal joint center of the right heel and a radius of 0.1 meters, a distal joint center at the right toe and a radius of 0.1 meters, and an extra target in the anterior direction using the right ankle joint center. Check Use Calibration Targets for tracking, apply and close the tab, and copy and reflect this for the left virtual foot. We'll now want to modify the segment coordinate system for the right foot, virtual foot, and change the anterior-posterior axis to +Z and the distal to proximal axis to -Y. We'll follow the same steps for the left virtual foot. Your modified lower body plug and gait model is now complete with all of the necessary modifications to account for the marker set.